So we're looking at angle launching with elevations today. And so it's one of these two cases, right? And again, hopefully you'll see the similarities back to when we threw an object straight up in the air and it came straight back down. In the top picture, right, they give us this 2 meters here in this picture. So we would make that negative because this would be my 0, up is positive, down is negative. Here, right, here's where 0 is, up is positive, down is negative. And so it lands up here. They tell you this is 3.5. I don't know why they put a negative there. Because the way we would do it, if this is 0 and it lands above, right, this is 1.5 meters above, and that's what I would put in for dy. Where here I would put in, right, -2 because it lands 2 meters below. So obviously wherever I took this picture from is setting it up the opposite way. So I don't know why they would want to do that. And so we're looking at, right, well, how do we solve for time when we have an elevation change? Everything else is going to be the same. Right, and so these are still our two main equations, the entire unit, right? And for over a month now, these have been our two equations that we've kind of gone to. But when we look at, and if we use the x equation to solve for time, we did that last bell work question with the General Lee on the cavalry on the, we used this, it was an elevation change, but we were able to get away with using the x equation to solve for time. And we use the x equation the same way. But when we solve for time using the y equation, when it was horizontally launched, that was 0, right? That was the first half of the unit. And then up until today, this has been 0 because we've had no elevation change. But now this is not 0, this is not 0, none of this is 0, so nothing is 0. And so, and here's the other key, we cannot use the range equation, right? Because for this to work, when I derived the equation for you guys last class, this was equal to 0. That's how I came up with that equation. So we can't use the range equation. That's one of the big errors that students make, is they look at these problems and they end up by using the range equation. We cannot do that. So just somehow make that huge on your paper that don't use the range equation when there's elevation changes. So if we look at our steps, step 1, still the same, find Vx, find Vy, right? So that shouldn't be a big deal. Step 2, if we can use the x equation, by all means, use the x equation to solve for time, right? Because it's the same regardless of what kind of projectile motion problem it is. And so we can count on x always looking the same. Even if it's an elevation change, nothing on here matters because elevations are in the y plane and this is an x equation. So just like the General Lee cavalry problem we did last class, right, we were able to do that, use this to find time. The problem is going to be as if, right, if we can't use the x equation to solve for time. So then we need to look at the y equation. And as I was mentioning just a minute ago, nothing in this equation is equal to 0, which makes it a quadratic equation. And so we have to either use the quadratic formula, you have to graph it, which you know is going to be a parabola, and find the zeros, or we have to find the time for it to go up, the time for it to go down, add them together. I think that's the long way to go. But when we did the other problems in the previous unit, some of you liked doing it that way. So essentially, excuse me, once you put in all the numbers, right, for dy, for VOY, we know this is going to be -10, so that one's easy, right? But this would have to be given, and this would have to be given, and we'll put in the numbers, but then we want to get everything on the same side. And so then it looks like what you learned in middle school, ax squared plus bx plus c, right? And it will always line up that this, right, will be because that's t squared, that's my x squared. So the -1/2 g is my a term, because I move everything to the left-hand side. And so when I put in a -10 there, -10 times -1/2 makes 5, right? So as long as we're on the earth, then my a is always going to be 5, which is the way I like to do it. This is always going to be different, right? And for us, there are problems, we won't do them. Again, it was kind of beyond high school. Like, we're always launching up, right? But we could launch things down, And so that would make, if we launch something down at an angle, that would make this a negative number to put in to begin with. Now, this negative sign is because, again, it's on the right-hand side of the equation right here. So when I subtract it over to the left, right, that's why there's a negative sign here. And so for us, this will always be a negative, whatever that number is, by finding VO sine of theta, because we aren't going to do these problems, right? They're a little bit harder, and for high school physics, they would never show up on any standardized test. Like maybe AP Physics would have to know that, but I didn't even do them with AP Physics. But then this, right, is just this height in this case, or again, it goes back to the first diagram. It's either a positive or a negative based on its displacement. And then we use the quadratic formula, right? And if we get a negative value, we always reject it, right? We only take the positives. So we would put in all our values here. And so what happens is, again, in this case, in this situation that I've drawn, you would get two numbers, but one of them would be negative, right? If the projectile was going to do this, so this would be the positive number, positive time. And so if you think about it, where would be the negative time? Meaning if this, whatever this was, when else would it be at, have that same negative displacement? Well, it would be this way if it went backwards, right? But obviously that's not even physically possible. And so this would give me a negative value for time, and we would reject it. So that makes it easy when we have a negative displacement that we put in to begin with. When you have a situation like this, right, where it goes like this, well, we're going to get two positive values. Okay, and again, this is the same thing we talked about before the winter break with straight up and down. We would get two positive values. One is right here. This is the bigger value, right? So that's the second value. The first value is going to be this one right here, the smaller value. There's very limited times where that would ever be the answer that you want. You would, to know that, you would have to you would have to figure that out inside the question based on how the question was worded. And back when we threw things straight up and down, the scenario I was able to give you was like if I was hanging outside a dorm room and you were throwing something up to me and I caught it on the way up, that would be time one. But if I didn't catch it and it went up, right, and stopped and came back down and I caught it on the way down, that would be time two. So you would have to infer from the words in the question which time you will want. But I would say 99.9% of the time we want this value of time. And so you're going to take all these values, you're going to plug them into quadratic equation and get the two values for time and pick the appropriate one. Right? And then once you once you do that, for these problems, dx is going to be the unknown, I would say, as far as I can remember, almost every time. Because dy is going to be given to begin with, right? There's no, other than finding maybe its highest point, which would be what we did on the bell work question. It has nothing to do with finding time today. But for dx, right, we, again, same steps, find vx, take the time we just found using one of our quadratic methods and multiplying it. And so it's pretty much the same steps that we've been doing for dx. And usually for elevation change problems, dx is what the problem is going to ask for. And again, this is going to make, this means we put in a negative, whatever this value is, right? Wherever, you know, whether it's to the foot, to the hand, or just this, you put in a negative for dy because this lands below, right? And then this, you put in a positive because, excuse me, it lands above. All right, let's do a problem so you see what I'm talking about. Now this one has how high, so that's an added step that it doesn't go, and again, how high is what we've already done. That has nothing to do with the fact that we're looking at elevation change. It's how long and how far, right? Those are the two questions that are different with how we're finding time, and then obviously how far is still the same, but it's based on our new way of finding time. So let's do this example, because if you understand this example, then you're going to understand every problem I throw at you, as you will see, because it's essentially going to ask for time and distance. meaning this distance. The only other thing it might ask is to go from here to here, right? So it could be from this point to this point, which is what you did with the bell work question. Or if we know this is 50 meters and we solve for this, I would add this value right here to 50 meters, and then we know that's how high it is from the ground. That would be the only difference. All right, so a water balloon is launched off a tall building. Right, you guys can obviously tell I like water balloons because I've used that as an example a lot. Right, which is when I was in college, right, that was in the 80s. When I was in a fraternity house, we would have little water balloon launching fights with neighboring fraternities. So we know that so again, we know we're always going to know the initial velocity of data, right? This goes back to day one. Neither one of these are going to be unknown for elevation change problem. But dy is going to be a negative 50, right? Because it starts 50 meters above the ground and it's going to land right here. So how high did the water balloon travel? All right, so the first thing I'm going to do, right, for an angle problem is I'm going to find, I'm going to try this today. I'm going to try to annotate. I don't know if you guys see the annotate bar, but let me see if it, all right, I'm going to do this first. So it means I'm going to take 45 times cosine of 60. And then I'm going to do VOY equals VO sine theta, right? So 45 sine of 60. Right, this cosine of 60 is 0.866, I think, right? No, it's 0.5. I get that backwards. 22.5. 38.97. So let's just call that 39. All right, so how high does it go? Part A. So that means I want to know here, right? Now, ideally, I didn't write this question, actually. This came from a textbook because I knew that diagram. Ideally, they would say how high above the starting point or the ground, right? So we actually have a reference point from which to really answer that. But I would, since we don't know time, this is where I would just use this equation, right? Because that's the same thing we did with the bell work problem, is we know that when it reaches this point right here, Vx is constant, but Vy is equal to 0. And since I know that is equal to 0, right? And so the idea is always look for similarities amongst the problems that we've been doing, right? Because we've used this equation to find this exact same thing before, right? Subtract over this first, then divide by 2g. 39 to negative 10 squared, divide that by 20. So I get 75.9. So that answer is from here to here, right? And so this would be above the building, right? And if it asked above the ground, then I would take that 75.9 or 76, and I'd add the 50, which would give me what, 125.9 above ground. So now when we're looking to solve for time, right, we have the quadratic methods, or you can solve for the time for it to go from here to here, right? And now that we know that it's going to go up 75.9 meters, but then, which you probably wouldn't use that distance to find time, but once you know that it's here, it's going to go from here all the way to here, it's going to fall 126 meters. You might use that to solve for time. I had to close the chat. It's 75, it's the highest point. Yeah, it's right there. but it's above here. That's what we calculated. This is 75. So if it asks for, like I was saying, if it asks above the ground, I would add the 50 plus the 75, and that would be 126 from here, but it's only 75.9 from here. So now when I solve for time, right, you could do, so let me do it over here. You could say, all right, time up. And I don't, some of you may like this way of doing it. I don't think I would do it this way, but there's no reason not to do it, right? We can use this because we know that equals 0, and we can solve this for time, right? And that will give me the time it takes for the water balloon to go from here to here. And then for the time down, right? This is what we did on the last test. Was the object was here, we launched it horizontally. It would be going 22.5 meters per second, right? And we calculated how long it took to fall. Same as like for the bullseye lab, right? How you solve for the time where this is equal to 0 at this point right here. We multiplied that by 2, divided by g, took the square root, we got time, right? This would be the time for it to go from here to here. This would be the time to go from here to here. We'd add them together, we'd get the total time. Maybe that's the way you want to do it. If you're just really uncomfortable with the quadratic methods. If it was me, and if I was you guys, because I know you guys have had years of using your graphing calculators, what I would do is I would use this equation, and I would say, okay, I know it starts here and I know it ends here. That means my dy is negative 50, right? Negative because it lands down here, which is, right, up is positive, again, down is negative. We've already solved this to be 39. We don't know time, 1/2 negative 10 t squared, right? And so what I would do is I would take this and make it like ax squared plus bx plus c, meaning 1/2 times negative 10 t squared. I bring it to the right-hand side, so it's 5t squared. This is positive on the right, but when I bring it across the equal sign, it's now negative, and the 50 is already there and negative. So what I would do is I would take that in my graphing calculator and graph it, right? And I don't know exactly. I know you guys have learned all the little tricks to graphing these things. I've long forgot them all. I know the graph is going to look like this in some way. It's going to be part of it's on the left-hand side and the negative x. This would be the time for the projectile to go this way. Can't do that, so that we would reject that value. This would be my answer. That's how I would do it. I don't, for no other reason than it's more fun to do it that way than using the quadratic formula. But we know the quadratic formula works, right? So negative b, so that means a negative 39 plus or minus b squared minus 4ac all divided by 2a, right? So there's 39 plus or minus. We know we're dividing by 10, which is always nice. And so you just have to do the discriminant part, right? That 39 squared, and it's 2 negatives, so it's plus 4 times 5 times 50. It's 2521 square root 50.2. So now again, I see 39 minus 50.2. That's a negative number. So I don't even need to calculate that answer. I'm just going to do the 50.2 plus 39 and divide that by 10 to get 8.9 seconds. Right? And so that's what that would be 8.9 right there. So you can see you got 3 different ways to do it. I like this way. I would, if it was me in my test, I would set up this equation. I would do this. I would sketch this and just say, here's my answer, right? And it shows that you know how to do it. And now the last part to this question, I've kind of run out of room. let's see if I can. I'm using, oh, so I was using the annotate bar there. So eraser, there we go. Looks like the annotation bar is better than in terms of the streaks. So now for part C, right? This was part B, this is part C, right? This is the easy part, right? We've done this. Dx equals Vx times T. Vx was 22.5 times 8.9. 200.7. That's a pretty good launch. That's almost 2 football fields with a water balloon. I don't know if that's realistic or not. That's a pretty, I know you can do on the ground, you can launch it 100 yards. I've done that before. On top of a building that's 50 meters tall, yeah, maybe that is possible. Questions on that? All right, as you finish up, so we know the initial velocity and we know the angle and we know that they hit a home run. And so it lands in the bleachers 8 meters above where it starts. So that's a positive end displacement, right? Where the other one had a negative displacement. And we just, this problem just says how far, right? So what is dx? And that's what most of these problems are going to ask. Just what is dx, right? It might ask, like the last one, how high does it go? We wouldn't, other than the fact that maybe you're the person to hit it, you're like, man, I really hit that high. How high did I hit it? We wouldn't care what that number was, but we would want to know how far, right? So we're going to find Vox and Voy first. So 24 cosine of 40, 24 sine of 40. 18.4, 15.4. All right, so now we're looking at time, right? Because in order to find dx, remember we cannot use the range equation, right? Because there's an elevation change. So that's a no-go. So we're looking for dx. That means Vx in time, right? So we know Vx. Oops. We know Vx, but we got to find time, right? Which is what most of these problems always come down to. So you could find the time for it to go from here to here and then to fall, right? Again, I don't think that's the way to go, but that's the beauty of having more than one choice. But all the other two choices are based around this equation. So, right, nothing is zero. So I know that's a positive 8. I've calculated that to be 15.4. 1/2 negative 10 times squared, right? Get everything on the same side. So again, 1/2 of negative 10 is negative 5, but I bring it to the other side, it's positive. Minus 15.4. I always get rid of the units when this is the one time where I get rid of units, right? So this is A, this is B, this is C. Now, when you graph this, if you're going the graphing method, right, if I had a way to show you what this looked like on a TI, I would do that. Right, but it's going to look like this because you're going to get two positive values, this one and this one. This is the one that you would want because the first one, right, would be, if this is 8 meters, this would be the second one. this would be the first one right there. This would be time 1, the smaller one. This would be time 2. Obviously, we want time 2. And so we wouldn't want that smaller one. All right, so negative b, so b is already negative. Plus or minus b squared 4 times 5 times 8. In this case, this part will be a minus, right? Last problem, it was a positive after, because that was negative. 15.4 dividing by 10, plus or minus. Now, when you know that the minus one is going to give me the smaller number, you could ignore that because you know that's not the answer that you're going to need. So I get discriminant is 77.9. I take the square root of that. I get 8.8. Right? So I add 15.4 to that. It's 24.2. Divide that by 10 as obviously 2.42. Right, and so that's the value for t I want to put in there. I use Vx. Don't know what happened there. 2.4. Multiply that by 18.4. Holy cow. No. Sorry, I was multiplying 24.2. I was like, that was 446 meters. That would be a monster home run. Let's try the right number. 44.2. That would actually be pretty small, right? So maybe we're playing on a little kids field.